everybody, welcome to the final video in our Module 15 videos here as we're exploring circles and a little bit more about specifically the angles that are formed with segments inside circles. So for Explain 1, we're going to be looking for the intersecting chords angle measure theorem, and that talks about exactly what it says. Two chords that are intersecting and the angles that are formed there, what the relationship is between those arcs and between the angles itself. So we've got two secants or two chords that are intersecting in the interior of a circle. Keep in mind where they're intersecting is important. So the interior of a circle is where that point E is. Then the measure of each angle formed is going to be half the sum of the measures of its intercepted arcs. So I'll just remind you that the intercepted arcs, remember, are what are cut off by the chords themselves. So AB would be an intercepted arc and CD would be an intercepted arc. And the relationship between the measure of angle 1, which is the angle that the chords form inside of the circle, is that it's half of basically the sum of the measures of its intercepted arcs, or another way to say it is that measure of angle 1 is going to equal the average of the intercepted arcs. Because that's what happens when you take two values, add them up and divide them by 2 or multiply them by 1/2. Average of its intercepted arcs. Okay, so that's the theorem we're going to be using. We are going to prove this one. We're not going to prove every single one, but on the next page, and I'm on page 830 right now, I would like to walk you guys through this proof because I think it works out pretty cool. So if we have AD and BC that we're intersecting at point E, again, what we're being asked to prove is that if we take the intercepted arcs AB and CD, angle 1 is the average of the two of those arcs. So here is our two-column setup for us. This is our given, and we are going to add in a new segment, draw BD. Remember, we're allowed to do that because through any 2 points there's only going to be one line. So there's our auxiliary segment BD, drawn in dotted line there. What we know is that the measure of angle 1, when we think about the exterior angle of the triangle, and I'll just kind of shade in the triangle that we're talking about here, that's this one. Can you see how measure of angle 1 is outside of that blue triangle? Well, it's an exterior angle. So remember, with our exterior angle theorem, the outside angle 1 is going to be equal to the sum of the two inside angles of the triangle that are far away from the one that the exterior angle is attached to. So that's what we call the remote interior angles there. So basically, angle EDB and angle EBD going the other direction, the sum of those is equal to angle 1. So that's important to know. Then we also know that because angle B, or angle EBD here, is an inscribed angle going this direction, we can see that it cuts off arc CD, and so its measure must be equal to half of arc CD. And then also, going the other direction, let's pick a new color here. Let's go with purple, let's say. And we're going to intercept off of angle D, or angle EDB, is going off of the intercepted arc AB. So because those are both inscribed angles, the inscribed angle theorem says that the measure of an inscribed angle is half the measure of its intercepted arc. And that's why we are able to say that since we know the sum of the two interior angles equals the exterior, then the exterior is actually equal to half the measure of arc AB plus half the measure of arc CD. And that's by substitution. And then if we go ahead and we just simplify that final expression in statement 6, the measure of angle 1 is actually half. If we pull the half out, a common factor of 1/2 out of both terms there is going to be equal to the measure of arc AB plus the measure of arc CD. And that's just using your distributive property in reverse. So we proved what we needed to prove. Pretty cool. All right, at the bottom of this page, you want to make sure that you are putting that theorem into practice. So find each unknown measure. Notice that the intercepted arcs, it might help to highlight those to begin with that they're working with are NL and KM in number 4. And then for number 5, since 58 is our given angle, the intercepted arcs are PR and SQ. So see what you can do with the average of the intercepted arc idea there for those two your turn problems. All right, now we're at Explain 2. I'm on page 832, and we have a different theorem that talks about angle measures. This time it's going to be formed by a tangent and a secant. And just like before with our chord angle measure theorem here, we have our tangent secant angle measure theorem that is going to introduce another value of 1/2 into the mix. But this time we don't have two separate intercepted arcs. We really only have one intercepted arc. So it's just that the measure of angle ABC is exactly equal to half of the arc measure that the secant and the tangent cut off, the intercepted arc. This one should be pretty straightforward. Let's see how we can do with this. As we go down to example 2, part A, we see that we have on this diagram over here, we want to find the measure of angle BCD. So that's formed by secant and a tangent. And it looks like the intercepted arc there is 142. So this is just a quick little calculation of 1/2 of 42 is 71. Then for part B, we want to find the measure of arc ABC. Notice 3 letters, so we want to wrap from A to B to C. Well, I don't know about you guys, but if I'm looking for the measure of that arc and I know that the angle itself is tangent, you can see the 90 degrees there at corner C, a vertex C. So the measure of angle ACD we already know is 90. Let's put that in. And if 90 is half of the arc, then that means that the arc has to be a semicircle or 180 degrees. Pretty cool. All right, let's see what you guys can do with your turns number 6 and 7 before we get to our final theorem. All right, the final theorem here is that the tangent secant exterior angle measure theorem. So we've got a secant and a tangent, but the corner of the angle this time is on the outside of the circle, okay? What we are seeing in that case, and again, it's on the outside of the circle rather than right on the circle with the tangent point, then the measure of the angle formed is half the difference of the measure of its intercepted arcs. So you see like 3 different cases there. I could have a tangent like I do in this first picture, a tangent and a secant, or I could have 2 tangents, or I could have 2 secants. Okay, so any combination of a tangent and a secant where our point is in the exterior, the corner of the angle, the vertex is at the exterior of the circle, we can use this idea. And that's going to be that it's half the difference of the measures of the intercepted arcs. So keep in mind again where those intercepted arcs are. For the first case here on the left, we would have an intercepted arc from B to D and also an intercepted arc from A to D. So you notice that's the bigger arc minus the smaller arc in the formula, and then it's half of that difference. For the second case, the intercepted arc is, the smaller one is EG, and then the larger one is actually the rest of the circle that's not EG. So that's from E to H to G, which is going to be a major arc. That's why we have 3 letters there. And so that's going to be half of, again, the larger arc minus the smaller arc. And then finally, the last case when we have our vertex at the exterior, but this time we have 2 secant lines cutting across the circle, that is going to be intercepted arcs KM and JN. So I hope you can see the 3 different cases that we might have being encountered in this situation. Let's look at the examples. In example 3, the value of x is what we need to find. So you can see as we're working through this problem, they've given us the value of the outside angle already of 25, and we are going to use the theorem that it's half of the bigger intercepted angle minus the little intercepted angle. Well, the bigger intercepted angle is 83, and the little intercepted angle in this case is our unknown, so we're going to keep it x. So 83 minus x is in parentheses times 1/2 is going to equal the angle 25. Now I would do in this algebra situation is I would multiply both sides by 2 to get rid of that 1/2. I would rather you guys do that instead of distribute the 1/2 through, because if you've got an odd number, you're going to get some decimals there. It's just kind of messy. So change it to just multiply both sides by 2, and then that'll get rid of the 1/2 for you. So we have 2 times 25, or 50, is going to equal 83 minus x. Doing some quick algebra, we get to the end there that x is 33. So that was a case of 2 secants cutting across. This is like this third case at the top. Part B is a little different. I hope you can see which scenario we're looking at. We're looking at the middle scenario where we have 2 tangent lines. Still our point is on the exterior of the circle. But this time we have a little thinking that we need to do as far as where those intercepted arcs are. The larger intercepted arc is clearly the 238 that is given to us, but to subtract the smaller intercepted arc, we actually have to do a little quick arithmetic here, because we need to figure out what is this arc that is left over out of the 360. So 360 minus 238 is going to give us 122 degrees is what that smaller intercepted arc is going to be. And doing that subtraction, we get 116. And then our final answer there, half of 116, gives us 58. So that's just 2 of the 3 scenarios. Hopefully you can see in your turn number 8, you're encountering the third one, which is the left-hand diagram. Follow that model and see what you can do with it. On the next page, page 834 here, you've also got your turn number 9 at the top, so don't forget to do that one. But with Explain 4, as we close out our video, I had promised you guys that we were going to be looking for a little bit of a summary here. This is a really amazing summary. This table kind of puts things all together for you. So our summarize the angle relationships. We can summarize the angle relationships in all of these different scenarios that we've encountered here by specifically looking at where the vertex of the angle lies, whether it's on the circle, inside the circle, or outside the circle. And so they've given us those 3 different scenarios. When it is on the circle, we have half the measure of the intercepted arc. So this is just a basic inscribed angle, and we know that that's half the measure of its intercepted arc. But we also know that if we have an inscribed angle which is formed by a secant line and a tangent, then it's just half of that intercepted arc as well. If we have our vertex formed inside the circle, like we do here where we have 2 secant lines that are intersecting, then that is going to be half the sum of the measures of its intercepted arcs. So the way that I remember that is that if we are adding the angles, then the vertex is on the inside. It's an add-in. And then if it is outside of a circle, here's again a half, okay? Hope you've seen that each time. Half, half, half. So anytime we're talking about an angle measure, we're always introducing that idea of 1/2. But in this case, we want to focus not on the word sum, but for outside, we want to focus on the word difference, okay? Or subtraction. So the way that I remember that, a little mnemonic to help you remember it, is that if I'm going to subtract or sub, my vertex is on the outside. So you add in and you sub out, kind of like you do in like a basketball game to get a sub in for you. You're going to say, I need to sub out. So that's just kind of a summary to help you remember what it is that you're doing with the intercepted arcs each time, depending on where the vertex is. So guys, that takes us to the end of our video here. Don't forget to do the final your turn. I'm going to leave you guys to fill in part A and B. Well, A is filled in, but I'm going to leave you guys to see what you can do with part B here, because it's a summary of those 3 different theorems. So make sure you're referring to the table on page 834. The summary that we just talked about, because we may be using a couple of these different theorems in this one problem. As you can see, we've got secants, we've got chords, we've got tangents, we've got all kinds of things happening here. So I'm going to let you go ahead and see what you can do for fill-ins for part B, and then don't forget to do the final your turn. And we'll see you guys in the next class.